Hello everyone, welcome to the week 9 problem solving session of the course Fundamentals of Micro and Nano Fabrication. I am Uditya, PMRF scholar from IIT Madras. So in this week, we are primarily looking at, we will be discussing 4 topics. The primary focus is on wet etching processes, and the first video is on figures of merit. Uh, the and we also go on with some of the jargons of wet etching, and then we see some wet etching basics, how the chemical reactions happen and what are the different chemical processes involved in it. Then we go directly to the recipes, the different recipes for isotropic and anisotropic etching of silicon. We also see something called the iso-etch curves, where we get to know that how the chemical components that are involved in etching, uh, how they are affecting the etch rates, and what are the different components and how the role of each component is. The last video is also on recipes, but primarily it deals, like, first part of it deals with gallium arsenide etching. Then you also get to know about something called etch stops, which primarily is a boron top layer of silicon, which essentially stops or impedes further etching. And then we got to know about defect etches, which are essentially recipes of etching that helps us in getting and differentiating defects uh, in a silicon wafer. And lastly, we dealt upon one application where we saw that how cantilever, how the role of etching plays a role in cantilever fabrication. So we will go directly to the questions. So we know that silicon nitride is a very widely used precipitating agent for silicon wafers, and so we have to mention what is a common etchant which is used to remove silicon nitrides. So these are some of the chemicals that are mentioned here: HF, KOH, H3PO4, and H2O2. So we have to tell which one of them is a widely used agent for removing silicon nitride. We'll go to the answer then. Silicon, that I mentioned, that it is a strong passivating layer and it is very hard to remove. So essentially we use hot phosphoric acid, and it etches at the rate of 10 nanometer per minute. So essentially this is the correct one. So yeah, for silicon oxide we go for HF as a etchant. This is like a common etchant that is used for silicon dioxide etching. Okay, so we'll go to the next one. So this comes from the isotropic wet etching recipe of HNA. So HNA is basically the recipe used for isotropic etching of silicon, which involves H means HF, N is nitric acid, and A is acetic acid. So this is a component of this mixture of 3 components. So here you have to tell the role of acetic acid. here, and this can be a multiple correct, so all the options that apply you can tell. So the options are promotion of ionization of nitric acid, promotion of formation of NO2, promote surface wetting of silicon wafer, and promote uniformity of etched silicon wafers. Let's go to the answer then. So acetic acid has like compared to like here like apart from acetic acid we could have used water. Yeah, so acetic acid has a lower dielectric constant compared to water, so which has a very high dielectric constant, and that's why and water we know is a polar solvent, so it promotes ionization of nitric it promotes ionizations. But here in this process we want that like the ionization means HNO3 breaking down into like H plus and nitrate, so that is avoided here because the ionization and the formation of NO2 are competing reactions. So essentially we want to we want this step to be avoided, and this one the option B, promoting the formation of NO2, to be enhanced. And that's why acetic acid plays a role, and it helps in like decreasing the probability of the nitric acid. So here the acetic acid helps in lowering the probability of ionization, and thus it helps in promoting the formation of NO2. So that is here. And also the surface wetting, like it helps because when we get this silicon wafers, they are hydrophobic in nature, and water tends to not stick on such surfaces. That's why acetic acid can help in like the recipe to be fully spread on the silicon wafer, and the reactions can happen uniformly. So essentially C and D options are interconnected, and because of the spread we also get uniformity of the wafers. So that's the reason. So the answers will be B, C and D. Okay, so we can go to the next one now. So iso-H curves, so we saw about the iso-H curves, and So you have to tell, so in iso-etch curves, essentially it is a triangle, and we have concentrations of each entity. Like here, if you take acetic acid, for the HNA1, I am telling, here you can take HNO3 and here HF. So depending on this, you will have such kind of curves which tell the H rate. So this is the iso-etch curves. So you have to tell H rate essentially depends on the concentrations of the minor entity, means the entity or the component that is present in a very less concentrations, or something that is present in a large concentration. So major means in large concentration, or minor means in less concentrations. We will go to the answer. So essentially here the diagram you can see that these lines, so here we see HF, okay, here this is the HF, this is the HNO3, and this is the dilute, that is acetic acid or water. This graph has both the things. So if we say this this green thing shows that the HF concentrations are very low, around you can say 5% or less than that. So here you can see the H rates are in this line, it is whatever is the concentration of HNO3 doesn't matter. The H rates would be 5.75 micron per minute, and it goes with the when we see about the HNO3 one also. With the HNO3 very less, around less than 5%, and with the varying HF concentrations, it essentially comes down to the same thing. So essentially the quantity that is in sparse concentrations usually plays a role, and you can go on changing the other components, mostly the effects will be very negligible. So it essentially depends on the minor entity, concentrations. The concentration of the minor entity. So we'll go to the next one. So we saw that there were various steps for fabrication of MEMS cantilever that was mentioned in the lecture, and so I mentioned all the steps here. The first starts with the wafer cleaning of using RCA, and then silicon nitride deposition using LPCVD or other CVD processes, then lithography, and then we saw that etching processes were there. And also we got to see that we first had them anisotropically etched, and then isotropic etching was done, followed by the stripping of the PR photoregister. So you have to mention, you have to tell that why two steps of etchings were done here, and what are the importance of it. So we'll get to the answer then. So till this step, till lithography, we get something like silicon here, and silicon nitride, okay, and some lithography. So essentially these are the, and we have developed the solution. So this is the PR. So now we go for silicon nitride etching. So first we etch it such that it is anisotropically etched. So vertically we will etch it. So it will etched like this. So essentially these portions it will be like this, and upon this now we are doing isotropic etching such that we get a undercutting here. So all these portions will be, so this as it is undercutting, so you will get and these portions will also get etched like this, and at some more point it will dissolve, and it will be, there will be no material there, and only material that is be left will be this one due to the undercutting, and essentially this part will be hanging, and then you can strip the PR and you essentially will get only the silicon nitride upon it. So that's why for getting undercutting we essentially require isotropic etching, and so these are the two steps. First is we getting a precise location where we want to go, and then after that we are going for isotropic etching such that we can remove the underneath layers also, and we get a kind of a hanging cantilever. We go to the next one. So this is a design of a device given here. So we have a silicon wafer, and upon that we have deposited silicon nitride, and then we have a strip of gold which is placed in it. Okay, so we can see, so you have to tell the fabrication process and using like how this structure can be made using a typical lift up process. Okay, let's go to the answer then. So here you can see that okay, let's start with the side view only. We'll start. So here, so essentially we will have steps that we discussed in the last one. That is, first we will start with RCA cleaning. So essentially we will only have a silicon wafer. We will have RCA cleaning, and upon that we will have so then we will have LPCVD maybe for the silicon nitride deposition. So we will have Si and X deposited on it. Okay. So here upon this we will go for so we will spin code PR upon it. Let's see, it is a positive photoresist. Okay. So then the next step would be going for the lithography. So for lithography we can see that what kind of masks you want here. So essentially for lift off we want these portions to be to be lifted off the surface here. So essentially we want these portions to be without chrome or positive photoresist. So we will make the mask could be So there it will be chrome, here it will be no chrome. So light will be exposed here, and so essentially after lithography, we have so here we can essentially use a negative photoresist. So for negative photoresist, we will have no chrome. So yeah, negative photoresist would be a better option. So in that we will have so we are exposing these two areas. So essentially the PR will be present in these two areas. PR will be there after developing. Okay, and then we can go for gold deposition. So we will go for gold deposition. So this can be done using sputtering. And then you will find that gold has been sputtered all over. So this SPR is a PR. Gold. And when we will lift it off using some PR strip, only the portion left here. So these portions will be portions will be washed off or stripped off the silicon nitride surface. So this is the process for lift off. Okay, so we will go to the next one. So this is another structure, and you have to tell the fabrication process involved in achieving the following device. So essentially the fabrication process is similar, but you have to tell how such vertical walls are essentially achieved in this, like how these walls are, which is very vertical, how they are essentially this is obtained through wet etching process. So and using wet etching, such structures are very hard to get. So you have to tell how such structures can be made, and what would be probably the fabrication process which they are using for doing it. We will go to the solution then. So essentially we start with silicon wafers. So the catch here is this silicon is of 110 orientation. This plane is 110, and what happens is that like this one is 111, and the other is 1 at the layer that is parallel is 110, and essentially this is what helps in getting such high such vertical walls. So essentially the process essentially is same. We go for RCA cleaning, then we go for PR coating, spin coater maybe, then we go for lithography. So for lithography, essentially if we say about the mask design, it will be essentially such kind of, so I'm only trying to and if we use negative photoresist, so essentially so you want these structures to stay. Okay, so these are clear. This no chrome, this chrome, oh sorry, this is chrome, this is no chrome. So essentially it is transparent. So we will get structures like silicon. Like if it is elongated, and then if we etch it using gent like KO edge, we will get such kind of structures. Essentially it will be like, because this happens because it is not finding, these gaps are very less, and it is not finding the below plates, so you will get such kind of structures. So this is PR, and then you can strip it, PR strip, so you will get this structure. So we'll go to the next question then. If any doubts are there, you can ask, and otherwise we can go. Let's go to the next one. So this is the question. You have to find the depth of etching for this. So you have to find the X here. So this is what you have to find, and so this is silicon wafer, and this is silicon oxide passivating layer, and this is 30 microns, and the total silicon is 540 microns. You have to tell what is the X, and so this is this plane is 111, and this what is the silicon wafer is the face of the silicon wafer is 100. So I think you all are doing it here. So whatever answer is, you can write in the chat box, and then we will also solve it. Okay, so one hint I can give is this angle is 54.7. We'll go to the answer. Yeah. So here we can see that this angle is, as I told, it is 54.7. So essentially this angle is also 54.7. So these are parallel angles. So essentially we have a triangle that is, we take it as alpha, where alpha equal to 54.7. And this is x, and essentially so we can, so this is the question. Yeah. So okay, let's do it like this. So if we have, we can, if we zoom it this way, so we will have this rectangle cutting like this alpha, and x is given this, so you can tell this is also x. Yeah. And the whole thing is 30, so essentially this is 15. So we can tell from trigonometry, we know that tan alpha will be perpendicular by the base. So essentially we have to calculate tan 54.7, 15 into value of x here. So let's calculate that. I will use the calculator on this. So tan 54.7 is coming out as 3.5 into it will be around 52.59 microns. So this will be essentially the length of X. Okay, I hope it is you all are getting the same value. If any doubts, you can ask. Okay, I think here I have taken this is in radian. Should I put it? So essentially it is in degree. So tan 54.7 is 1.141 into it will be essentially 21.19 Okay, so we'll go to the next one. It's the last question. So this is a shape that is drawn on a mask, and it is used for having KOH etching. So we have to draw a side view of that hole, like after etching, how that hole would look like. And it is that we have to tell that this the parallel to the page, like if this is the silicon wafer, this side is 100. These are these planes are 100 planes. Parallel to the page. So if we have slices of the planes of the silicon are 100 plane. What is the material? So this is something that we are visualizing from the top. So this silicon wafers, these round wafers, are on the you can assume it to be on the screen. We will go to the answer then. Yeah. So essentially, if we assume this to be on the wafer, essentially we saw that we only get what is like the etching after it etches, like this is the 100 plane, and we will so when we expose from the side view, essentially get is the, like if we see this inside, we will get this here silicon, and when we after we etch, we will get like this. Okay, and this is the 100, and these are the 111. So irrespective of the structure, essentially cuts out in this in such rectangular kind of or square kind of fashion. Yeah. So that's all for today, and we will close the session. If any doubts, you can stay, and otherwise you are free to leave. Okay, so we will meet in the next problem solving session. Next week, same time, and we I think deal with the problem week 10 videos. Yeah. So thank you all for joining.